sometimes it could be worthwhile to know whether a differential equation even has a solution and if that solution is going to be unique before you just jump in and try to attack a particular problem. And that's what this handout and presentation is going to be about. So the simplest approach for a first order differential equation is to get it into this particular form here, and if we can show that P and G are both continuous functions on a neighborhood that contains T0, which is the initial time point, you could think of that for the initial condition, then that means that a unique solution does exist. So let's tackle a few problems that are going to make use of that approach. So let's take a look at number 1 here. It is already in the general form. You have a y prime plus a p function times y equals a g function. And so when I look at this, I need to look at the continuity of p and g. So I notice that p of t, which is 2 over t, is continuous for all t that's not 0. So as long as it's not 0, we're okay. If I continue to take a look at the g function, which is 4t, this is continuous everywhere. So now I need a neighborhood that contains the point 1, because that's what our initial time point is. So when I look at this and I know it can't include 0, I'm going to consider the interval where t is greater than 0. And notice it's strictly greater, it's not greater than or equal to, because it can't be 0. So consider the interval t between 0 and infinity. Since p and g are continuous on this interval, which contains the initial condition t0 equals 1, we know that a unique solution exists. So that's how you apply this particular approach when you can actually get the general form like this. Let's practice with another example. Go to problem 2, and I've already developed a solution for it, but I just want to talk you through it. So in this case, we do not have a differential equation in the general form. We need to put it into that form first. So if you divide by 4 plus t squared, you're going to get the general form, which I've written here. And so now we look at p and g separately. And so p, which is 2t over 4 plus t squared, is continuous everywhere for all t. You're not including imaginary numbers, so that's fine. We're just considering real. And g of t has the same lack of restriction, so it's continuous everywhere also. So since they're continuous for the full real line, for t from negative infinity to infinity, which contains the value of -2, our initial time point, that implies that a unique solution exists. But what if you have a scenario like problem 3, where it may not be feasible to put it into a general form. And so already in this case, it was conveniently given in a dy dx equals form. Now let's go back to the first page to talk about this scenario, because this is the case where in general, if you can't get it into that general form, what you can do is you could look at the y prime. Now y prime is actually viewed as a function of x and y, or t and y, whatever your two variables are. And so we're going to be looking at the f function. If f is continuous in a neighborhood that contains the initial point, then we know that a solution exists. But we also need to look at the partial derivative of f with respect to y. In case you are unfamiliar with how to do that, it is pretending that anything that isn't y is constant and just take the derivative of anything that has y in it. So if you had x times y and you were taking the partial derivative with respect to y, it would just be x, because the derivative of y is 1 and x is like a constant in that case. So we want to look at the partial derivative of f with respect to y, and if that is continuous on the same neighborhood that contains this initial point, then we know that the solution is not only, it doesn't only exist, but it's also unique. That's what we're going to do for problem 3 here. So let's take a look at it. Looking at the y prime that was given, I could see that x's are only in the numerator, and so for any x, that is not going to cause any discontinuities or issues, but y is in the denominator, and I could see that when y is 1, we're going to have a problem. And so it's going to be continuous for y below 1 or greater than 1. In particular, I'm going to look at this neighborhood here, x along the real line, y less than 1, because that contains the y0 value of the time point of 0, and the y of -1. So now I know a solution exists. To take the partial derivative of f with respect to y, the 3x squared plus 4x plus 2 divided by 2 is constant, so you have a 1 over y minus 1, or y minus 1 to the -1 power. So when you take the derivative of that part, you get the negative y minus 1 to the -2, or squared when you put this in the denominator. So that's how I got this as the partial derivative with respect to y. Notice that this is continuous on the exact same neighborhood. It doesn't have to be, but it is in this example. So for any x and for y not 1, we are going to have a continuous partial derivative with respect to y. So you can find a neighborhood for which both of these are continuous, and that means the solution also exists and is unique. There's one problem left, which I've got here, and we want to go through the same process to determine whether this particular IVP has a unique solution or not. So we have our y prime, which again is f of, I'll say ty, but you could claim xy, is y to the 1/3. Now this I could see is continuous for all t. There's no t restriction, and I could tell that it'll be true for any y also. Now we have this as our neighborhood, which contains the initial point 0, 0, and so we know that a solution exists. But the problem at hand is to determine whether it's going to be unique. So that means we need to look at the partial derivative now. So the partial of f with respect to y is going to be 1/3 y to the -2/3, or y to the 2/3 on bottom. And it's going to be better to put it on the bottom, and you'll see that in just a moment, because we want to know the continuity of this, and so this is continuous t anywhere on the real line, but y, I'm just going to write y not equal to 0. And hopefully you see what the issue is. The issue is that our initial condition is that y of 0 is 0. So we want y to be able to be 0. But in this case, y cannot. And so that tells us that even though we found that a solution exists, we now know that since y cannot be 0, the solution won't be unique. And that's it. As always, there are practice problems below for you to do at your leisure. Enjoy.